In our final lecture in this week, we will discuss glass-glass modules. First, we will give an introduction and a market overview. Then, we will consider the advantages and disadvantages of glass-glass modules compared to standard glass backsheet modules. In glass-glass modules, the polymer backsheet is replaced by a second glass layer at the rear of the PV module. The glass thickness in glass-glass modules is typically 2 mm per layer. In glass backsheet modules, the front glass is typically about 3 mm thick to provide sufficient amount of mechanical stability. So in terms of glass volume, a glass-glass module has roughly a 30% increase. According to the most recent International Technology Roadmap for Photovoltaics, about 1/4 of all PV modules sold in 2021 were glass-glass modules. The projection is that this market share will double by the end of the decade, and glass-glass modules will be the new standard technology in the 2030s. These glass-glass modules are often bifacial. This increases the energy yield due to also using irradiation from the rear side of the PV module. Note that while most glass-glass modules are bifacial, that there are also monofacial variants. These have a wide rear EVA layer or a wide ceramic layer to serve as a rear reflector of the PV module. Likewise, the typically monofacial glass backsheet modules can also be bifacial by applying a transparent backsheet at the rear. Manufacturers often offer longer guarantee lifetimes for their glass-glass modules. The lifetimes are in the range of 30 to 40 years, which is compared to 20 to 30 years for glass backsheet modules. This difference is a result of the better protection for the solar cells. For example, a lower moisture ingress from the module rear can reduce corrosion of the metal contacts. Additionally, glass-glass modules reduce the cracking of solar cells due to mechanical stress. All this contributes to the lower power degradation rates, which increases energy yield over time. Additionally, glass-glass modules often contain higher efficiency solar cells or more durable encapsulation materials such as polyolefin, which increases this trend but are not directly a consequence of the glass-glass nature. Higher energy yield and a longer lifetime result in a lower environmental impact for glass-glass modules. Additionally, glass-glass modules are sometimes made of semi-transparent modules with wider cell gaps to install in carports, roofs, or other situations which benefit from semi-transparency. Glass-glass modules also have several disadvantages, most notably the increased weight by around 30% due to the additional glass volume. This typically increases their weight to above 25 kilograms, making them difficult to handle for a single person. It also increases the transport weight and cost, as well as the requirements on the installation structure. On the other hand, the lower water vapor transmission can be disadvantageous since reaction products can be trapped inside the modules. This can cause acceleration in the degradation of the encapsulation materials, thus resulting in discoloration and corrosion of the cell metallization. As discussed in the last lecture, using more stable encapsulation materials, such as polyolefin instead of EVA, can help to reduce these issues. Another drawback is the higher material cost of the glass compared to the polymer backsheets, which results in generally higher prices for glass modules. To recap today's lecture, we introduced glass modules, which account for about 1/4 of today's PV modules, and the market share is projected to double until the end of the decade. The advantages include a generally longer lifetime and higher energy yield, resulting in a lower environmental impact. The increased weight and cost are the main disadvantages of this technology.